So these are the answers to question 5. Part 1, you have to work out the new value of the car. So that means we substitute in t equals 0, which gives us v equals £20,000 as its starting value. Part 2, find the value to the nearest pound after 3 years. So we substitute in t equals 3, which gives us v equals 20,000 e to the negative 3 over 10. So you need to use your calculator to evaluate this. In case anyone hasn't been able to locate the exponential button on the calculator, you want shift and then the button that says ln, even though it looks like it says in. It's usually next to the sine button and next to the log button. So this gives us this value, 14,816.36, ... and we need to round this to the nearest pound, so that's £14,816 to the nearest pound. So part 3 asks us to find the rate. Now for the rate of change, that's the derivative, so you need to find dv by dt. Now you will be doing much more on how to differentiate exponential functions in the year 13 content on differentiation, but for the moment, and this is in the content of the video, if we know that y equals k multiplied by e to the ax, and k and a are constants, which means they are some kind of numerical value, really they represent numerical values, then differentiating dy by dx, you get k a e to the a x. So if we go back to our derivative of v with respect to t, this will give us 20,000 multiplied by negative 1/10 e to the power of negative t over 10. So that formula will allow us to calculate the rate at which the value is falling. Now for part A, they want us to calculate the rate at which the value is falling when the car is new, which means when t equals 0. So if we substitute in when t equals 0, this gives us dv by dt equals 20,000 multiplied by negative 1/10, which comes to a value of negative 2,000. Now what does this actually mean? Well, think about the units. It's dv over dt, so the units of this rate are the units of v, which are pounds, over the units of t, which is years, so it's pounds per year. So what this means is that the value of the car is changing by £2,000 per year, and because there's a negative sign, this tells us that's a decrease in price of £2,000 every year. If your rate of change, which is what this is negative, it tells you that the value is decreasing, or the number is decreasing. How much is it decreasing by? It's decreasing by £2,000 per year. So what's happening in part B? We're asked to calculate the rate at which the value is falling after 2 years, so when t equals 2. So when t equals 2, dv by dt is equal to 20,000 multiplied by negative 1/10. We can actually, in the gradient formula, simplify this here. So we could have written this as negative 2,000 e to the negative t over 10 up there, which would have been a bit simpler. Negative 1/10 multiplied by e to the negative 2 over 10. Let's work that out on the calculator. This comes to a value of negative 1,637.461 ... or negative £1,637 per year. Now, there's a bit of phrasing here that I think we have to be careful about, because the question says, find the rate at which the value is falling, not the rate at which it is changing. So really, I think in part A, we need to say it's falling by £2,000 per year, and in part B, I think we need to say that it's falling by £1,637 per year. We don't need to include the negative because it's implicit by our use of the word falling in both cases. So part 4 asks us to sketch a graph of V versus T. Please make sure you use a ruler as you sketch your axes. So time in years on the horizontal, value in pounds on the vertical. We know we start with a value of £20,000 and then the graph approaches 0 as T approaches infinity. Now for the last part of the question, it asks us to comment on how good we think the model is. Well, for one thing, the value of the car appears to ultimately approach 0, but actually any car will still have some value over time because it can always be used, for example, for parts or something like that. So that's not necessarily a realistic aspect of the model, that ultimately the value of the car appears to become 0 or as close to 0 as possible. It may also be the case that the value of the car will depreciate a little bit more quickly than the rate given by the model, which is only losing £2,000 per year. Question 7, part 1. How many settlers land on the planet initially? So P is population. Initially means T equals 0, and this very simply gives us P equals 100. So that's 100 people. Part 2 requires us to sketch the graph of P versus T. So T is time in years and P is the population value. So our graph would look a little bit like this. So we start with a population of 100 and then we see our exponential growth like this. So part 3. Find the rate at which the population is increasing after 10 years. So rate means we need to differentiate. We need to find dp by dt, the rate of change of the population with respect to time. So that's 100 multiplied by 0.05 multiplied by e to the 0.05t. So that gives us 5e to the 0.05t. Now, we want to find how the rate increases after 10 years. So t equals 10, which gives us dp by dt, which is 5e to the 0.05 multiplied by 10, and that gives us a value of 8.2436, etc., which we'll say is 8.24 people per year. So that's how the population is increasing, by 8.24 people, so 8 and a few. Now, part 4 of this asks us what is the actual population after 50 years. So we need to substitute in t equals 50 into the equation for the population. So 100 e to the 0.05 multiplied by 50. So this comes to a value of 1218.249 ... So we could say 1119 if we wanted to the nearest whole person. Now, part 5 of the question says, what is the minimum number needed to settle for the population to be at least 2,000 after 50 years? So I will do this up here. So part 5. So we want the population to be at least 2,000 after 50 years. So in this formula, P equals 100 e to the 0.05t. Remember, 100 represents the initial number of settlers. So in part 5, they are asking us to find out how many would we need initially to get the population up to 2,000 at least after 50 years. So I'm going to swap this 100 for a constant k. And the rest of the formula stays the same, e to the 0.05t. So we're now not starting with 100 people. We're trying to find out how many people do we need to start with for the population to be at least 2,000. So let's imagine the population equals 2,000. It's never going to be exactly 2,000, but let's just say that p equals 2,000 for simplicity. So 2,000 equals k multiplied by e to the power of 0.05. Now the time they've given us is 50 years, so let's substitute that in. So we've now got to solve 2000 equals ke to the power of 2.5. So simply divide 2000 by e to the 2.5 and you will get your value of k. Now, remember the question actually said at least 2000. Well, what we could have done back up here is we could have made this an inequality around here. So an alternative way of setting out my working here for this would be to say that I want ke to the 2.5 to be at least 2000, so greater than or equal to 2000. So k has got to be greater than or equal to 2000 over e to the 2.5. Because we're not trying to make the population exactly equal to 2000, we're trying to ensure it's at least 2000. So inputting this into the calculator gives us k must be greater than or equal to 164.169. So because we have to start with a whole number, an integer number of people, k's got to be greater than or equal to 164.169. So that means the minimum value of k is going to have to equal 165 people. So that's how many people you need at the start if you want the population to hit at least 2000 after 50 years. So question 8, we are told that the mass of the radioactive substance fermium-253 is given by the formula m equals m0 e to the negative kt, where t is measured in minutes and m0 is the initial mass. So the value of m when the time is equal to 0. So the half-life of a radioactive substance is the time it takes for half of the mass of the substance to decay. So that means that if half of the mass decays, that means that the new mass, m, must equal a half of m0. And what they're telling us is that this happens when the time is equal to 3 minutes. So if we substitute this information into this equation here, so we are saying that the mass is half of its original value, so m is equal to a half m0, and this is equal to m0 multiplied by e to the negative 3k, because t is equal to 3, we've substituted that in. Now you can see the m0 cancels immediately and we're left with a half is equal to e to the negative 3k. Now you will learn how to solve exponential equations in the next lesson. That's why question 8 was meant to be an extension question for anybody interested in reading ahead, but you actually need the next piece of knowledge, the next lesson, in order to be able to solve this. So think about when you use logarithms. Think about your previous knowledge of logarithms. For instance, if you were asked to solve the equation 7 equals 2 to the power of x. Now, one way of solving that is to say that log to the base 2 of 7 is equal to x. Well, we do something similar here, except we take log to the base e. So I would say log to the base e of a half is equal to log to the base e of e to the negative 3k. Now, of course, on the right-hand side, this cancels to give us negative 3k. Now, on the left-hand side, as you will find out in the next lesson, there is a special way of writing log to the base e. It's called the natural log, ln, or ln. So ln of a half is equal to negative 3k, and then we can simply rearrange this result to get our value of k. So k equals ln of a half divided by negative 3, and we can work that out on the calculator. You will see that the ln button is next to the sine button, and if we input this into our calculator, we get a value of k which is 0.231049 ... which we can round to 0.231 to 3 significant figures.